Rocky and Werewolf and Abtainer communities and say, let's make sure that all the changes that are needed upstream for the Raspberry Pis, as of a few versions of firmware ago, can be put into netboot mode, so we can actually, in principle, make Werewolf work as well. Now, I haven't done it yet, but I think all the pieces are in place. And I've talked to several people in the community, and they're excited. So I think that partial to this new schedule called Flux from limited Raspberry Pis. There are at least 3 different classes of CPU cards you can put into this thing. All right, we're here at Supercomputing 2023 with the smallest cluster in the show floor, at least the smallest cluster that's running enterprise Linux. It's right down here, and it's a Raspberry Pi cluster that's running Rocky Linux on 2 nodes, running the latest Fedora 39 on the head node, and it can actually accept Jetson Nanos or other types of CPUs. The whole goal here is to take the enterprise high school or used for software development or with exactly the same software. So here, we'll stop now, and you need to get onto the All right, so here we've got a Turing Pi 2 version 2.4 motherboard. It's got 4 Raspberry Pi CM4 modules, and I've actually tacked on an extra Ethernet here on the node 4, just so I can have a dual-ported head node like I have on a real cluster. Eventually, I will actually build a separate head node out of a little $25 router card, so the cost to get into this stuff is extremely low, but it's running Fedora 39, as of 3 weeks ago, it boots natively on Raspberry Pis. So that means that I have all the runway needed to build the rest of the software stack. I've already talked to several of the Werewolf developers. We think we can make Werewolf work on that setup. Eventually, of course, it will go downstream to the Rocky product line, to any of the Enterprise Linux product lines, so we'll be able to run Enterprise Linux on this setup. It's early days yet, but I think we're really excited. That's probably enough.
That was awesome. That was awesome. Cool. I think, yeah, this was a good, thank you for letting us have all of that space.
So they've taken that whole process of Okay.
The way that would almost work for us is there would be a way to identify ID action.
So it all depends on what you're
And then Buzzball, or not counter, but to this app thing, and Buzzball would set that up for your copy. That would have to be something submitted, and then they would decide, okay, you're allowed to log this way. Now, I'm not saying it's a blanket thing, but the way it's used.
So that's yeah. So
Anfang Mitte nächsten Jahres.
Yes. Precisely. It'll be something. It'll be something that's in like proximity that you have to echo, right? And so Buzzball would just see, okay, this job needs to have access to that while this job is running out. And take it off.
So what
And it's like that this way.
and since if it was at one point today,
Yeah, I have me too making
I don't think it's supposed to be out for giving. It has to be taking yes. Yeah, they're just in a style.
So it's all hardware based.
That goes in.
exactly. We have even have like a little target.
But it does stand out.
Okay, so
All of this data into that volume. Into the job. So yeah. So you get that much faster.
That's where you use that.
So you talk to so yeah, so he's great. So what's the trend this data coming in from this object solution? Source is here. Destination is the file on the job, so you should perform it now. Job.
Yeah, I would like. Yeah, kill me for saying that.
That needs to create a volume. Which is going to be your first job. And to go into that volume. Yes, we'll go now. Pros and cons. Pros job runs. System administrators will say, no access. So it'll go back to storage. Itself. That's it. So you can lock it down. After
absolutely. It runs as a separate job that is part of the graph.
Or in any action. And your factory use cases. And your workflow describes the same, but for jobs. Something that I know that is, for example, their jobs fail a lot. They haven't multiple jobs on Twitter. Some of them fail because of so they just go over some bad. That doesn't fit perfectly into it, and have to redraw the job.
Me rendí primero que ella. Job 3 fails for whatever reason.
And I retried. Just
The answer right now is no.
how important is that to me? I don't know. I just think new features, like you were asking, like what features would be good to think about. Like that's one. So
See Fuzzball, if you find job output, you can see each job working parallel.
Seems a little disconnected.
No, you're saying the whole workflow. I think you could just do the what's up.
Probably trying to figure out an offering in an angle.
Right. That's true. Like they do.
So they're not actually up with a pretty low, or you have to go to work to get it. You are still getting they're going to need mostly compatible. Really? Versus yours is sort of as close as possible.
I think we talked about this before. behavior things are quite well. Like a manager that also help you. Cycles is going to install.
Took a little doing. Still works.
Want to automatically configure it. I was like, if it's hard enough, you want to configure it. Just
Because that's my little test.
So what you're talking about.
We have all the drivers for all 10 jobs. Up and running. I can run it. Videos in my pocket on the side. Intel. It works great.
So, like, from a workflow perspective, we would want to have the concept of continue from possibility versus like create a new job that tries to inherit the state of the old. And so, if we like allow the job to fail, and we set it up in a way where we don't do cleanup, and we allow the option to either do cleanup or do some sort of modification at a reasonable point, like not try to modify it, so you have to grow just downstream modifications. And then wants to get an email that this failed, and this is why. Do you want to update it? Do you want to? Yeah. So you can.
Hello? Yeah, I can hear. Well, you tell me. Good. Hi, my name is Scott Campbell. I'm the product manager for PBS Professional. Been working with Altair for the past 18 years on PBS, and today I would like to talk about the advantages of OpenPBS and Altair PBS Professional once it will be integrated with CIQ's Fuzzball product. Just as a quick introduction to Altair for those who may not be familiar, Altair is a very large company where simulation, HPC, and AI converge. What we mean by that is Altair's sort of flagship, probably most well-known, at least historically, business unit is the HyperWorks division, which is simulation and design platforms for automotive, consumer products, aerospace, etc., doing finite element analysis, crash simulation, and so on. We have Altair RapidMiner, which is a relatively new acquisition in the data analytics and AI platform space. And then Altair HPC Works, which is our HPC and cloud platform stuff where the majority of what I'll be talking about today fits into that arm of the business. Before I go there, though, in the HyperWorks sort of product development side of things, Altair has recently released our Radios crash solver as Open Radios to the community, and we've been partners with CIQ in launching that. CIQ has been tremendous help there in containerizing Open Radios, including Open Radios in Rocky Linux, etc. So there's other areas outside of HPC that Altair and CIQ have been collaborating in the past few years. Drilling down into the HPC Works side of things, I'm not going to go through all of these, but this is essentially the portfolio of products that we currently offer. Today I'm mostly going to be talking about PBS Professional as under the workload management side of things, but over the past few years, Altair has acquired different companies in the workload management space with Altair Accelerator for the EDA space, the Grid Engine. Altair Grid Engine used to be Univa Grid Engine, Oracle Grid Engine, etc., very strong in the life sciences space. Liquid scheduling is one of our new solutions for connecting multiple clusters together in new and novel ways for unlimited and unparalleled scalability. Come check it out at our booth if you would like to know more about that. In addition, we have a variety of products around user accessibility for job submission, admin control of HPC resources under PBS, and job workflow analytics. We have monitoring solutions, including Altair Insight Pro, which is a new topic that I will talk about briefly at the end here, as well as different. These are I/O profiling tools, and this is a very complex job dependency manager tool that comes out again from the EDA space. So in addition to PBS Pro, we have the community edition of PBS, currently called OpenPBS. It includes a lot of the foundational technologies that have made PBS a pillar of the HPC industry for the past 20-odd years, including scalability up to tens of thousands of nodes and millions of cores, robust policies for deciding on what the right work to run is and where to run it so that business goals are met, fair share is met, whatever sort of interdepartmental agreements that exist at an organization can be met. It's very resilient, failover, no single point of failure. When jobs fail, they're handled in a sane way so that PBS doesn't lose track of them and they can be rerun and their same results can be captured on a rerun of the job. There's a very flexible framework plugin where during critical events in the life cycle of a job, Python hooks can be embedded into the system that are executed with good visibility into the job data structures, control over some of the job attributes, and so on. Same for nodes, depending on the event in question. Implemented via that framework, we have a health checks framework, so you can make sure certain devices or certain file systems are mounted before greenlighting that node to start jobs. You can make sure that users exist, libraries exist, whatever it is you want to check. And in the past, we've been voted OpenPBS has been voted #1 HPC software by HPC Wire readers at previous supercomputing. So we've got OpenPBS and we've got PBS Pro, and why might you want to choose one versus the other? Well, it all comes down to, I'm not trying to start religious wars here between open source and commercial, but there's in certain industries there's risk avoidance in a lot of commercial, car companies, for example, or an aerospace company, versus the sort of risk takers and early adopters that want to be on the forefront of what you can do with an HPC management system. So the experimenters versus the 100% reliability, and we think the current PBS Pro and OpenPBS dual licensing solution addresses that in a way that hasn't really been seen before in HPC. So I'm going to talk a little bit more about Altair PBS Professional specifically, and why you might and what it offers above and beyond OpenPBS. So just an overview of the capabilities. A lot of it is what I already talked about with OpenPBS, because there is a lot of fundamental crossover between the two. Some of the differences we get to in capabilities are the ability to simulate, which I can talk to in a few minutes, about simulating changes into your scheduler configuration or job workload or node configuration or even node quantity, to simulate with your actual job structure, job data, what the scheduler would do differently if it had a different situation. Additionally, we have an allocation management system. There's some cloud bursting capabilities. So with PBS Professional, you get regular patches. We have additional security features in PBS Pro, enterprise security features that are not included with OpenPBS, including TLS encryption of all network communication and full SE Linux MLS support, which enables government agencies to run multiple different classifications of jobs on a shared hardware resource. We have container support for Docker and Singularity with PBS Professional. Podman and Aptainer work as well if you've done an alias. We're going to revisit that soon, but that's where things stand. We have a high throughput scheduling module that can increase the throughput tens of thousands, hundreds of thousands of very small, very short jobs. If you have a bursty workload like that, there's a high throughput computing module that works directly with PBS Professional, taken from one of the other, the EDA scheduling domain that I had spoken about earlier. Budget management. Outside of the core workload manager, you can allocate budgets of different resources, so storage, compute, CPU time, etc. Accrue that over time, set budgets and goals and limits for the year, for the quarter, whatever the charge period is. Charge different amounts based on how and where the job runs, and then do all post-pay budgeting or post-pay model so that it doesn't do any enforcement while jobs are being scheduled, but you can do accurate reporting and charging back after the fact, or you can have all these policies be enforced so that jobs will not be allowed into the system or will not run when they get into the system, in addition to the normal complement of PBS Pro queue and server limits. Simulation, I'll talk about that more in depth in a second. Cloud bursting, PBS includes a cloud burst module that can burst based on workload suitability, resource requests, etc., into all the major clouds, so AWS or OCI, Google, and Azure. PBS provides robust GPU integration, so turnkey configuration for device isolation for NVIDIA GPUs, topology-aware device detection and scheduling, so that you get GPUs that are associated with the cores that are closest to them, setting up the environment and collecting GPU usage information from things like DCGM, for example. Again, not to go into too much open source versus commercial product rabble-rousing here, but a lot of times you're shifting the cost from upfront to later when you have a support. And Altair has been known for years for our excellent support teams based all over the world, so you can get support in your local language. And again, increased quality assurance, so more regular patches, improved uptime, fewer unhappy users. Coming up in our next release for version 2024.1, this is coming out in January, we're introducing a GraphQL interface to cover common job and query, job submission, job alteration, and node and job query task. So essentially covering the qsub, qstat, qdel, and qalter and PBS nodes commands. This is great. This provides another avenue for things like Fuzzball, where we can integrate other technologies seamlessly into PBS using a modern API. We have the CLI and so on. so the admin can, or the application can generate tokens that have expiration dates and so on, and do all of the normal token management things for Web API access. Back to workload simulation. And this is a feature that's unique to PBS Pro and allows admins to, again, take their current jobs in the queue and change the scheduling policies that are in place, change the amount of nodes that are available to the scheduler, and sort of just vet out any potential change that you want to make to your scheduling policy or your cluster, and make sure that it's going to have a beneficial impact on your workload. Using a different Altair product in our HPC portfolio called Altair Control, you can actually also do those same sort of simulations going back months and months into your past history, your counting log history. So you can run, with PBS Pro, you get the from now forward sort of simulation or look ahead simulation, and with Altair Control, you can also do look back simulation. And again, no impact on productivity. It runs much faster than, it's a simulated reality, so you can run your simulations much faster than it would take to experiment and possibly have a negative impact on your cluster to find out you shouldn't have done that. Coming next, we have a Altair Insight Pro. This was just announced yesterday. It's our latest generation of monitoring and reporting solution for your cluster. So it can take data from jobs, from system metrics, cloud telemetry, etc., and different products from the Altair portfolio, including these I/O profiling tools that I had been talking about, and integrate that and synthesize all the data and answer common questions for admins that want to know about who used what and when, what did they leave unused. Was the system being used efficiently? How long? What did job wait times look like relative to their execution time, and so on. And I have a few example charts here showing cluster usage by queue. So what was the unused, number of CPU hours, GPU, so that some of these advanced scheduling capabilities and reporting tools and so on can be available with fuzzball workload generation and workflow management on top of it. There's other solvers are as well. We've been really working closely with CIQ, and it's been great over the last few years. So I can take any questions or anything else, but thank you. Thanks for having me in your booth, and thanks for your time. Yeah, go ahead, please. So the question is about how does the cloud bursting work? So actually, in this case, that's actually used because we are using the actual scheduler to say, here's the instance. The scheduler has a menu of all the different instance types that have been pre-configured in the cloud bursting admin GUI, so it knows that I can do this instance size and that instance size and so on, and it simulates, well, if I bursted, I'm trying to burst on behalf of this job, if I bursted 4 of these instances, would that job run? If the answer is yes, it'll burst them, and it can do that multiple times to reduce cost and hit whatever targets you want, but it is actually leveraging the PBS scheduler to make that decision via the simulation technology. Does that answer that question? Yes. The scheduler will provision resources on the cloud based on the configuration of the bursting engine, right? So jobs that have specific resource requests, jobs that reside in a certain queue, for example, may be eligible for running in the cloud, but some jobs may be on-prem only. And the provision... Absolutely. So the question is, after the job finishes, will the cloud resources... Anything else that we should talk about? Okay. No, thanks a lot for having Altair at your booth, and we're looking forward to doing a lot more collaboration in the future with CIQ. Thanks. Bye.
Hello? Hello? Alrighty. Hey everyone, my name is Tanner Brown. I'm a systems architect on the Sandia National Labs HPC testbeds team. Today I'm going to be giving a little bit of background on what we do on the testbeds and how we are using Werewolf and Ansible for a lot of our system automation. So Sandia Labs, we have three main branches of our testbeds team. We have our kind of true testbeds. It's a lot of smaller systems, kind of the newer cutting edge stuff that we're working on. A lot of heterogeneous architectures. It's pretty low availability or kind of low readiness. We're getting a lot of systems that we're kind of plugging in straight from vendors and letting loose our kind of expert users on to test, break, let us fix it, and kind of make sure that everything is working and kind of determining where the future is going that way. A lot of the times it's on kind of open networks. It's still internalized, but pretty open availability. Then we have our next kind of branch, which is our Vanguard systems. A little bit larger scale, still experimental since it's under the testbeds kind of scope. More focused efforts on advancing this new technology that we're testing from the testbed side. A lot bigger kind of user base that we're working with here. Kind of expanding it from our expert users and a little bit more polished of systems here. And really the idea is to increase the technology landscape. A lot of these resources on the Vanguard systems are DOE systems, along with the NNSA Tri-Labs, most of their resources there. And then our third branch that we're working with is the application readiness test beds. These are kind of just smaller twin really systems of a lot of the bigger leadership class systems like Trinity and Sierra that are out there. They're advanced system technologies. They're really built to support the code teams with their CI/CD pipelines, things like that. With more production-like availability, still not production level, but what we strive for production level support. Down on the bottom here, we see our test beds as Sandia Labs as a group. We're more on the left side of this, higher risk, but a lot more diversity in our architectures. And as you go more and more towards the production-like systems, you get greater scalability, but kind of less risk and kind of lower diversity. So the Hello, there we go. So the kind of true test beds branch that we work on, it's a lot more hardware and software. That's really experimental pre-release stuff. We're getting straight from the vendors before they've really even tested it. We're testing it for viability and the really early evaluation to see if it's a possibility for future systems. Pre-release CPUs, GPUs, other accelerators. Now that we've got a lot more FPGAs, our announcement with Next Silicon, and really a lot of new storage systems, things like that. Then we have our application readiness test beds. Like I said, it's small to mid-scale, normally 1 to a few cabinets of the really leadership class systems that really support the code readiness teams. A lot of the debugging and performance tuning happens on these systems before it's really users are going to really big systems to use. Often they're testing their pipelines on these machines, dedicated for debugging. They've got a lot longer reservations than the big systems, so people can test their stuff here before moving it to really big systems. And then we've got a lot of the really advanced like systems operations activities, research on new ways to develop and manage systems. That's when Werewolf and Ansible comes into play. We're testing all these workflows and stuff and seeing if they're viable solutions for the really big systems that are out there. Werewolf, Fuzzball, CI/CD pipelines, a lot of different cloud technologies, cloud storages, things like that. And then a lot of container-based stuff. Container-based images, we're running containerized system services, Podman, Kubernetes containers, pods, and stuff for system services, and then a lot of containerized workflows and ephemeral storage. So the true test beds aspect of this, a lot of the hardware stuff, it's pre-release CPUs, it's stuff that has high bandwidth memory, on-chip memory, stuff that uses a combination of both. A lot of the early H100 GPUs, GPU RAID accelerators, stuff like Grade and things like that. A lot of machine learning and data flow accelerators, stuff like the next silicon cards like that we're working with now. And then a lot of FPGA stuff, Linux, Xilinx, Bitware Molex, things like that. And then a lot of the software side, Kubernetes, HPC, both on the management side of things and also on the user side of things. We're using Werewolf for the HPC, the provisioning. On the test beds, we're using Werewolf on most of our clusters now for node image management and things like that. We're experimenting with Rocky Linux with 8 and 9, which is replacing CentOS for end of life. So a lot of that kind of stuff. A lot of the node images from container images, and then we're using Ansible to configure our containerized node images, things like that. So then we have more of the application readiness test beds. One of our new Cray clusters, Tachi, we've been working on quite a lot. They're the small to mid-scale versions, things like Trinity, Sierra, Crossroads, El Capitan. We run these systems exactly the same as the big production systems. So we're able to use these to test things before they're put into production. So a lot of researchers use these for testing their codes, debugging, performance tuning, things like that on these smaller clusters. So they're able to take that code and run it on the big systems before they're reserving the entire node on the big clusters and things like that. And the nice thing about this too is we're able to use these systems to run patches and do things like that before it's put into effect on the big clusters. And it also gives us the ability to do a lot of like the power capping, CPU trimming, things like that on here. Yep, so it's mirror systems. It's all the same hardware, but just in a smaller scale. So it's, say you have a system that's 5,000 nodes on a big system. We're getting maybe 50 to 100 nodes on a smaller scale. We run it in the exact same way, the exact same management systems like that, so that we're able to test on a smaller scale before deploying it to a production environment. So now that you have some of that background, it's a question of why we need all this automation. So on the test beds, as you can imagine, we have an insane amount of systems and different architectures, a lot of different hardware and software churn. We're constantly testing new hardware and software. And if you think about it from a system administration point, it's a nightmare. So I mean, just in advance, like a really diverse pool of different clusters and node types. We can have a single test cluster that's 10 different node types. It's got different hardware, different FPGAs, GPUs, things like that in the nodes. Utilizing different pipelines to try and automatically like generate these images. We're doing a lot of testing with Ansible, GitLab, container images, regression testing, things like that. And then also we're building and testing our node images as container images. A lot of times we're pulling Docker images, say of Rocky 9.2. We pull a Docker image in. We can run our Ansible plays on our container image, and then we can mirror that or copy our image within Werewolf and make changes to that so that we can distribute different node types across our cluster. So a big thing is containers. We're using GitLab, like I said, mainly for our Ansible work, for our different version control and things like that. We can have a base Ansible configuration where we're pulling a ready-to-go Rocky 9.2 bootable container image. We can run our Ansible plays on it to configure it for our network and things like that. And then once we put that image into place in Werewolf, we can make copies of it that are specific to our system and cluster. We can make specific changes in either runtimes or overlays inside of Werewolf, and then we can deploy those different images across a lot of different nodes. It makes the management a lot easier for us so that we can boot a lot of different container images. We can do testing on specific nodes to make sure things work. Once we have a working image, we can modify the container image so that it'll boot across the rest of the nodes with different runtimes and stuff. And we're testing this as a test beds. We're prototyping this whole process so that we can try and deploy it to our different Vanguard and possibly CTS and ATS. Yeah. I'd say it's a lot quicker because our test beds team is only 5 or 6 members right now. So I mean, if we were constantly building stateful disk images, doing a lot of stuff like that, and actually modifying an entire OS image on Rocky for each individual system, it would take a lot longer. We wouldn't be able to do as much as what we do now. A little bit of what we're doing for what we're kind of calling HPC 2.0. We're doing research on new ways of deploying and managing system and user workflows. So using fuzzball and things like that on the management plane and also on the user plane, running system services and things out of pods and Kubernetes, using Werewolf and fuzzball, our different CI/CD pipelines for our file systems and different cloud technologies. Our system images based on containers, and then ephemeral storage, things like that too, where we're creating pods for storage as it's running in Kubernetes, and then it's able to wipe out that storage after each run. An example here, say we have a 1,000 node cluster. We have our 10 node management plane. We're getting all of our CI/CD pipelines, our Jenkins, GitLab, things like that. They're going into the fuzzball orchestrate over the network, spawning Kubernetes pods. All of this is running on Rocky Linux. Then it gets sent over to the fuzzball substrate where it's running Werewolf for all of the node images. And then it's going to all of our different cloud storage and things like that. So I think that's about all I have for now. My team lead is going to be giving a fuzzball demonstration after this, so if you guys want to stick around for that. And yeah, and if you guys have any questions. So we're mainly using Ansible to configure all of the little things that we need for the Sandias network and all of the different.
My name is Forrest Burt. I'm a solutions architect here at CIQ. I've been with the company for about 2.5 years now, and in that time I've worked a lot on our fuzzball product. So I'm here today to talk just a little bit about CIQ and about our to talk a little bit about our CIQ company and what we do here and about our fuzzball solution that we have. I've got a little demo for us that we'll run here in a little bit, but in general I've got a few slides, stuff like that to show you guys first, but then we'll jump right into the GUI and take a look at what we've got. As I'm sure many of you know, we are CIQ. We have a full stack of HPC products from the operating system to the applications level. So Rocky Linux, Werewolf, Aptainer, Ascender, different things like that to meet the needs of your enterprise or HPC organization. You can talk to us all more about these products if you'd like to. I won't dally on this too much. This demo is on Fuzzball. So Fuzzball is our big HPC orchestration and pipeline kind of workflow engineering app that we've been working on for some time now. Basically, right now, we're all very familiar with the Beowulf model. This is traditional HPC. This is what we've been doing for a good 20, 30 years now. Most traditional HPC systems that we have today are built based on this architecture. Standard flat head node with a whole bunch of flat array of compute nodes underneath it. This is a fantastic model. Obviously, this has powered our science for a good 20, 30 years now and has been one of the primary drivers of everything HPC. So this is a fantastic model, but kind of as we get into the 2020s and we kind of start to see HPC advance a little bit, we've started to see changing needs within both HPC and enterprise that have kind of led us to develop a new model that we call HPC 2.0. HPC 2.0 is kind of implemented in our Fuzzball product. And why exactly are we seeing kind of this move away from traditional HPC? We have a few different things going on at the moment. First off, we're seeing use cases becoming more and more complicated. Science is advancing, pipelines are getting more and more complex. Just in general, things are always getting harder and harder to compute. So use cases are getting more complex, and we're finding that we need the ability to orchestrate larger and larger clusters in order to make these things continue to work. We kind of have this split model at the moment where HPC has all of the high-performance management, Kubernetes, that type of thing that they've been establishing for years that helps manage these massive large systems that we're starting to need in HPC. So in general, we kind of see that split. We see things like AI becoming a bigger and bigger use case everywhere, and the need for larger and larger clusters to support that. Kind of in general, we've always had this model where we half expect users to be a little bit of a computer scientist themselves, even if they're a domain scientist. We'd like to move away from that and get more of a focus back on users being able to just focus on their science and just have us, be helping them set that up, but not telling them so much how to do it based on, kind of what we have to do right now with interacting on the Linux command line, things like that. So we'd like to get away from that. The cloud is a big question in HPC. Of course, there's a lot of interest in that, a lot of kind of be able to integrate that with our on-prem systems. So that's something big that we're looking at. Supply chain security, we're all using containers. We're trying to bring those into HPC, that type of thing. That, especially recently, has had a big push to kind of make sure that we can track back where software comes from with SBOMs and have more signing and verification and things like that around containers. So we, in general, like to be able to do a little bit more with those in HPC than we can do right now. And just in general, like I said, organizations that have never seen themselves as HPC organizations are starting to consume this, and HPC organizations are starting to need orchestration and management like they haven't needed before. So we have a few different driving forces that are kind of leading us to building out this new version of HPC, like I said, HPC 2.0, and kind of the Fuzzball product. To give you guys basically the architecture diagram of what we're working on. I see my slide is a little off there. One of the biggest things about Fuzzball is that we're integrating Kubernetes with HPC. I think we've all kind of seen some of the batch computing efforts over time that have come out with Fuzzball and HPC. But in general, these all kind of fall afoul of the fact that Kubernetes was never developed as a batch computing engine, and there's overhead that happens if you're trying to run HPC apps in pods that decreases your performance. In general, Kubernetes is a little bit of a Byzantine concept in HPC in general. We're all very busy. So being able to sit down and actually get into Kubernetes and figure out how you could integrate it in your HPC environment is difficult. Yet Kubernetes is ubiquitously used in the enterprise. Basically anything you interact with on a daily basis is probably Kubernetes under the hood one way or another. So why aren't we using it in HPC? Like I said, because there's traditionally never been an integration between Kubernetes and HPC that has used the best practices of both and been able to integrate those effectively. So with Fuzzball, we are building kind of an all-in-one automation platform around HPC that allows you to, instead of running this more conventional HPC stack, run this Fuzzball orchestrate piece of software in kind of a more standard Fuzzball or Kubernetes microservice type architecture. So essentially what we're looking at here we have a control plane for our fuzzball product that runs somewhere up in the cloud. This is on some type of managed Kubernetes like EKS, something like that on AWS. In just a moment, the demo that I'll show you is going to be up on EKS, so that's where that's running. So you have some type of managed Kubernetes that this control plane is running on. The control plane ultimately consists of a series of microservices that provide the overall fuzzball kind of orchestration stack. Ultimately, what this gives you is the ability for users to codify their workflows. That standard input data comes in, pre-processing, run your analysis, post-processing, results go out. You can codify those pipelines regardless basically of what type of vertical of science you're working with. We've done AI training, CFD, FEA, a wide variety of different use cases on this. Regardless of what your use case is, I'm so sorry, I lost my train of thought. We have, like I said, users can, like I said, put together their workflows, codify their stuff. They send it into the API endpoint for the fuzzball cluster. Everything in fuzzball, like I said, there's no SSHing onto a cluster. There's no having to get onto a login node or head node or anything like that. Everything in fuzzball is API driven. So users are able to either use a CLI or a GUI to interact with the cluster. And essentially take these workflows that they build in YAML or with our graphical builder, send them into the fuzzball cluster, and then this series of microservices kind of breaks apart that workflow into its component parts and orchestrates the rest of the running of it. So there's a workflow engine that takes all the different requirements, sends them out to the other microservices. There's a data mover that handles any S3 transfers or other data transfers that need to happen before the job can run. A volume manager that sets up any that type of thing that the workflow will need to run. Everything in fuzzball is based on containers, so all jobs that users are running are done out of a container. So there's an image service there that manages that. One important thing to note is that Hello? There we go. One thing to note is that none of the actual applications are running inside of Kubernetes. Hello? None of the actual applications themselves are running in Kubernetes pods. Only the orchestrate services themselves are running in that. So we've kind of implemented this best practice of only using Kubernetes for the microservice orchestration plane, and then that does all the other interactions that a workflow needs in order to run. So for example, when a user's job needs some resources to be able to run out on the cloud, our provisioner service takes those requirements, sends that out to AWS. It spins up an instance based on those APIs. It lands the AMI on it that has our custom container runtime fuzzball substrate, and is able to land a container and a command on that and start running it, independent of needing to have a Kubernetes pod doing that, with Kubernetes itself just kind of monitoring those instances and waiting for them to be done. And so yeah, you have the control plane, the stack of microservices that are providing what exactly we call fuzzball orchestrate in this. On the other side of it, on your compute resources themselves, you have some type of operating system. Of course, we're real big on Rocky Linux. And then our custom container runtime fuzzball substrate. As I said, when nodes are spun up in this out on a cloud provider, this is installed onto the nodes, and it's a custom container runtime that the rest of the cluster can then drop a container and a command onto and have run on those arbitrary resources. So functionally, that's a service. And yeah, overall, the process, like I said, ingress, you've got volumes, you can persist data. You've got volumes that you can use to persist data back and forth through between jobs in a workflow. And yeah, end-to-end, this is kind of the concept of fuzzball orchestrate. So I have a demo that we are going to take a look at once I move over to that. Is there anything else I wanted to cover? Nope, I think we're good. So to actually give you guys an example of what we are working on here and what this looks like from a user perspective, I will go ahead and log into our instance here. Oh. There we go. So as I said, everything in fuzzball is all API driven. There's no users logging in, having to interact with the command line, doing that type of thing. it's all API calls versus a cluster endpoint. So everything you're seeing me, for the most part, except for like the graphical editor here, for the most part, all these cluster management operations that you're going to see me do here are all things that can also be done via the command line through the Fuzzball CLI. It just so happens that we're here in the graphical one because that's more fun to look at. So this is the actual workflow screen. Like I said, these are runs of different HPC pipelines, essentially. Whether that's some type of CFD job, some type of AI training, some type of, like I said, represented is just in the YAML, so if you know the syntax, it's easy enough. But we provide the graphical builder to make it easier, like I said, for those domain scientists that don't want to have to learn as much of the Linux command line and to just unpack those tarballs. And then we actually run our example training script for Llama 2. So if we want to see what this actually I'll go do this. This is the actual workflow editor. So you're looking at essentially a graphical interface to put together a HPC workflow end-to-end. So this is the same type of thing that people might be doing when they're writing scripts, except for that now we can do this graphically and all wired back into the cluster, so we can run this when we're done on the resources that we have here, and that we've defined here. I'll show you that in a moment. You can see that when we want to define a job in Fuzzball, we have a few different things that we can add. First off, over here is a command. So this is essentially a shell built in, a compiled application, anything like that you are looking to have an MPI job or a task array, basically. Task array being that embarrassingly parallel type architecture, multi-node being MPI, and also GasNet. I don't know if anyone uses PGAS, uses the Chapel programming language, anything like that. But this also has support for that as a multi-node implementation alongside MPI. We can also edit the environment of a given job. So all jobs in Fuzzball execute out of containers. And in this case, we are accessing a GCP artifact registry with just a username and a basically access token here. This is wired back into HashiCorp Vault, so you can store secrets within this cluster and then have them be templated out at runtime via this type of format. So when it gets to the server side, it gets inserted there, and users never have to keep their credentials in their workflows. We can mount storage volumes to these, so we can have essentially scratch space for our different jobs and workflows and things like that to use, or our different jobs as a part of the workflow to use. If we go to volumes, you can see where we've defined that. We're calling this the Llama Barn. But you can see I've got this ingress configuration here, where I'm basically just providing my AWS keys in a region, and specifying that I want this tarball pulled down with that model file, and doing the same here with the tokenizer. We could add an egress if we wanted to push back out graphs, results, another like fine-tuned model. We don't have one here, but we could configure that same thing just by pushing it back up to an S3 resource. Like I said, everything is done out of a container. We can mount volumes. We can also decide the resources that any given job needs in order to run. So this one needs 8 CPU cores, 28 GB of memory. This one right here, and you'll notice that this is a directed acyclic graph of execution. So as long as you have no cycles in this, you can essentially build this dependency matrix, essentially as arbitrarily complex as you need. If we go look over here, we can see a different resource request along with one NVIDIA.com GPU that we're requesting. This is our device plugin, so specifying device files, drivers, and libraries for device, and giving Fuzzball the ability to bring that up and address that if you have those resources on your compute nodes. We also have support for certain FPGAs and things like that, but in general, this is working for GPUs at the moment. I don't have a demo of it right now, but we also have the ability to spin up isolated network namespaces and use a port forward to bring things like Jupyter Notebook up on this. So you can run this workflow. It starts a Jupyter Notebook out on AWS resources, and you can use this port forwarding tool via the CLI to bring a port from that. So you can then, localhost 8888 and get access to what's. We'll go ahead and as a part of that job. But resources we're actually going to be running this on is contained in the definitions. So for the moment, we're focused on the cloud vertical with Fuzzball. So it works on AWS. We're working on bringing it to other clouds, especially GCP at the moment. But for the moment, it's very operable on AWS, up to and including like the Elastic Fabric adapter and things like that. You can see that most of our compute sources here are instance definitions from AWS, so like a P3.2x large with a certain AMI there. So as I said, our provisioner service will reach out, match the resource request that a user requests in their job with the instance that best matches it. Provisioner will reach out via AWS, spin up an instance matching that. This AMI with our fuzzball substrate runtime is landed on that. The instance is then leased back to the fuzzball cluster. The job scheduler is able to take that instance, or give it to the workflow, land the container on it, land the command on it, and boom, your workflow is running. And so these are how you define different compute definitions. That's a P3.2x large, so a GPU instance. We can do, T2.2x larges for testing. Essentially any arbitrary instance you want to add to this. It's essentially just adding the AMI, the instance type, and any devices that it has on it that it needs to be aware of, as far as the definition goes. We've got secrets stored in here. You can see different AWS access keys, container registry access keys, things like that. As far as container registries go, this, like I said, interacts with anything public or private. As long as you can give it some type of username and a account credential, you're good to go. There's kind of a account structure that works with organizations. We call organizations and accounts. So in this case, CIQ is our organization, and we can have different accounts down below that all have their own users, their own secrets, their own definitions, workflows, etc. So you can imagine that as something like you have one fuzzball instance for your university, and then different labs have their different accounts, users, etc. out below it. This is going to basically run in the background here, but just to show you one last thing. We can retrieve the logs from a workflow. Those are automatically captured by fuzzball, except for on this one, apparently. That's interesting. See if it grabbed it on one of these other ones. Huh. That's odd. When I was showing this earlier, there was logs there. Maybe I'm on the wrong workflow or something. Anyway, so as things like that are printed, they get collected. There's a log tab that prints that live. There's also a terminal that you can get directly onto the instance that the job is running on. I would show you that, but it's going to take a few minutes to get to this run llama example here at the end. These untars are pretty quick, but here in a moment, I might be able to log in there. So yeah, that end-to-end is what fuzzball is. It's kind of in a closed beta right now, so we are taking partners in for our SaaS platform kind of selectively. But if you're very interested in talking to us more about it, I would encourage you to come and have a conversation. That is the fuzzball platform. Are there any questions I can answer? What's up? So the question was, right now it's mostly on the cloud. What are we thinking for on-prem? Yes, at the moment we are focused very heavily on the cloud vertical for this. We have a decent amount of sophistication in the on-prem case, but for the moment, with everything we've got going on, we're mostly focused more so on the cloud side, as that's a little bit, I don't want to say low-hanging fruit, but it's a little bit more approachable than some of the on-prem stuff. But we do have a great level of sophistication there. We've got, for example, an automated installer for on-prem that can basically turnkey bring up a fuzzball cluster there. But we kind of have that at select partners at the moment that we're working with there. But yeah, a lot of sophistication on it coming soon. Yeah. Ultimately, our goal with fuzzball is to enable hybrid computing between all of your data centers. So we'd like you to be able to have a single pane of glass that includes all of your cloud resources, your East Coast data center, your West Coast data center, your European, APAC, et cetera data center all put together in such a way that users can codify what they need to do, submit that workflow to one single endpoint. Fuzzball is aware of all these other clusters that you have that are also on Fuzzball, and you're able to score based on cost, resource availability, more esoteric things like custom parameters, carbon credits, stuff like that, where exactly that workflow should run on all those different clusters that you have wired into that. That's kind of our roadmap. We've got a little ways to go before we get there, but like I said, we've got some sophistication on-prem. We've got a lot of sophistication in AWS. Our roadmap for next year or so is all about improving our cloud offering and starting to provide that federation layer so that we can have that true hybrid computing model between on-prem and cloud resources.
one more workflow they have to learn in addition to all the other workflow languages. For example, Nextflow, SnakeMate. Do you have or are you planning to have any integration with, say, a Nextflow?
So the question is, what's the plan for the integration with other workflow engines that are out there? Yeah, obviously there are a lot of them: WDL, SnakeMate, Cromwell, all that type of stuff. At least in the Nextflow case, something that we're looking at is, for example, how they build executors for different, Kubernetes, AWS, things like that. Nextflow has a yeah. So that is Fuzzball. Like I said, MPI, task arrays, even PGAS support and stuff like that. And that's the platform. Thank you all. And once again, thank you all for attending.
I'm just curious, how big is your dev team behind Fuzzball?
About one of the things that we have in it, which is the mainline stable kernel, or builds of the mainline stable kernel that we have for Rocky Linux. So it's a pretty simple demo today, but please feel free to stop me and ask any questions that you might have. So as I mentioned, we'll be using two CIQ products, or hello? Yes. We'll be using two products that CIQ supports at least. A product of ours, Mountain. The other is Rocky Linux, which of course is a community product that we have value adds on top of. So what is Mountain? Mountain is our content repository and content delivery mechanism. So right now we're supporting RPM packages predominantly. It has Yum repositories that you can subscribe to in it. So you can use Yum or DNF to subscribe and get packages just like you would with any other package repository. But with that, we also support OCI registries, so we can push OCI containers and kind of the whole stack of that up into a registry to supply that as a product to our customers. And we also can support CIF container images in that same registry. So if you're using Aptainer or Singularity or even Werewolf, you can pull those images directly down from Mountain from a subscription that you have with your CIQ support contract. But the future of the Mountain platform is to expand it as kind of a hub for our partners. So not only CIQ products would be in there, but we would want to have ISVs as well as a growing catalog of open source software pre-built, ready to go in subscriptions for you to run so that you can integrate Fuzzball deployment or pull it directly into Aptainer and not have to build those containers. And in the kind of parallel future, we're developing an edge mirror version of this. I think I just heard that this is basically done. The kind of first, well, now second version of it that we're going to start pushing out as a product, but it's not available today. But the idea here is synchronize products down, be able to add your own packages to the edge mirror that you deploy in your environment to not have to go out over the internet for a cluster of nodes. This is what it looks like today. This is kind of not the admin view, but an admin's access to it. You know, list of products. Each one of these is some kind of registry or RPM repository. You log into this web UI, generate an access key, and then put that in with a Mountain CLI application that will demonstrate. So I mentioned a couple of these things, things that you can find in Mountain today. For our partners that we're doing Fuzzball beta testing with, you can get Fuzzball out of here for certain on-prem deployments. We supply Aptainer and Werewolf images here. If you're familiar with Werewolf, it uses, or it can use OCI container images as its node image. Pull those directly out of Mountain. and import them into Werewolf directly. I actually skipped a little bit. AppTainer and Werewolf packages for the open source stuff, but if you want builds from us, you can get packages from there. You can get Werewolf node images. We do supply CIQ custom patches and builds for various products and patches on top of Rocky Linux. In the future, not in the future, I'm thinking of the kernel LTS release. We mark certain versions of Rocky Linux as long-term support and backport security patches into even numbered point releases of Rocky Linux. So those are available there. But last on our list here is the mainline stable kernel, which is a value add that we provide on top of Rocky. So just to be clear about what I'm talking about, if you go to kernel.org, you can see the releases of the Linux kernel as they come off of the developers. And they have mainline, which is literally the head of development. All patches that are accepted by Linus Torvalds are in that main line, but then on a release cadence, there's a stable release of that main line. And so that's what we're taking. We're taking that and building it in a version that integrates successfully with Rocky, is built to work with Rocky, but has more up-to-date hardware support and additional kernel features than what you would normally get in an enterprise Linux kernel. For comparison, if you're not familiar, the enterprise Linux kernel distribution strategy is to take a specific kernel release, keep it stable at that point from an ABI standpoint, and then for the next 10 years, backport patches onto it, maintaining that compatibility, the security posture that you need. So the Enterprise Linux 8 kernel is 4.18. The Enterprise Linux 9 kernel is 5.14. They were released in 2018 and 2021 originally, respectively. But the mainline stable kernel that was in the CIQ repository when I prepared this, we'll see if there's a newer one when we run the demo here, was released in August. And that's the kind of access to the most recent kernel that you can expect through this offering. Not to put too fine a point on it, but if you're still on CentOS 7, it's running Linux 3.10, which is more than 10 years old now at this point. So just another pointer. It's time to get off of CentOS 7. So this is where we will switch over to an attempted live demo. One-handed. Yeah, that's the worst part. I'm realizing now that I've left my notes over here. Not that I can't just do this, but it's good to have a backup plan. Oh, and now I've disrupted that. Okay. So what we've got here, we've got two windows here into the same system. This is, a VGA console off of a cloud provider. We're using Vultr here. You can visit their booth down that way, in fact. And it's running Rocky 8. And you can see that here in this SSH session. And we want to take it to mainline stable kernel. So the first thing that we need to do is download this Mountain application. It's a simple command line binary. And in just a moment, I'm going to put the mic down so I can type with two hands. Excellent. So that's the first hard thing to type. So what we're getting here is a package that's on a completely open Yum repository. I guess it's not even a Yum repository. We're installing the Yum repository here. But this is a package that anyone can install that's just, on our website. And this enables a CIQ repository that we can then install our Mountain application from that repository. Is this big enough? Can people see this here? Okay, great. So now we have this Mountain binary. And this is our gateway to the CIQ Mountain SaaS platform. So the first thing we need to do is attach it to our subscription. Like I mentioned before, what you would do is go into the web interface and you just say, I need an access key, and you get it. For the purposes of this demo, I've already pre-populated that in an environment variable, so I don't have, but this is one command. More interesting than the grass growing. I mean, Mountain is the delivery mechanism that we use to give it. So there's Mountain, the SaaS platform. That's where we serve it out of. But in theory, you wouldn't need to use the Mountain command line application to get to it. You use that to generate the Yum configuration the first time. At that point, you could take it out and put it in your configuration management or like that. So that is intended with the platform. It's not in the platform today. Yes. Yes. I'm afraid I don't have a time for it. Hello? What I can say is that the Mountain platform and the enterprise Linux ecosystem that we're building on top of Rocky is kind of #1 priority for us right now. It's where most of our attention is going. So I expect soon, but oh yes, within the next year, absolutely. Any other questions? It's like the opposite of a dial-up internet connection. There we go. So, package is done installing. Not too exciting at this point, but at that point, we can just reboot our server. We can watch the reboot happen in our console over here on the side. If we look carefully, we can see that it's already showing us that it's going to boot into that 6.5 kernel. And here it is. Hopefully our SSH is back up and running. Yep. There. And from here, we can see that we're still running Rocky 8. But we're running this much, much newer kernel that was built a month ago. So, pros and cons here. This new kernel should have, more security patches integrated, newer hardware support, newer kernel features. In theory, you have new file systems. The Enterprise Linux kernel doesn't support BTRFS, for example. This kernel will. You won't have the BTRFS user land, so we'd need to also bring in packages for that. But it's a gateway to much more functionality. But there's a reason why this isn't the default kernel, and that's because when we talk about the Enterprise Linux platform, we're talking about a kernel compatibility layer that will allow you to bring in out-of-tree kernel modules as well. Things like a Lustre client or a Lustre server, other file system clients, Mellanox driver, NVIDIA driver, things like that that are built against the kernel for that platform. So one of the things that CIQ is doing is this trade partnership between CIQ, SUSE, and Oracle to try and drive adoption of a new standard for what Enterprise Linux is. And one of the things that we're hoping to prioritize there is newer kernels and access to newer kernels as part of that standard. So that's my presentation, that's my demo. As before, if there are questions, I'm happy to take them. But otherwise, thank you for your time and for sticking around.
Hello to the CIQ audience. The strategic marketing manager at Panasys. I'm going to be talking to you about a little curveball for what you've been probably listening to relative to Rocky Linux and other CIQ, but it's within the HPC ecosystem. We do parallel file systems. We do software, the stack. We do hardware appliances that we provide to the market. And I'm going to talk a couple stories, one on modern HPC and where we see that market going. And I'm going to make an analogy from my past. So we've been around since 1999, since the inception really of a lot of the parallel file systems. In fact, we're the first parallel file system to commercially deploy on Linux. We have our founder was co-inventors of RAID at UC Berkeley, Garth Gibson. And from that, you'll see this story about resiliency and reliability because it's like built into the DNA of the company. Everything else we talk about, performance, manageability, all that, usability, all that is riding on top of the fact that we have this reliable system that's very self-healing, fault tolerant, and fault prevented. This is effectively a block diagram of PanFS. So the idea is that you have client applications. We have our direct flow client that would run on a Linux, and we'll talk about later about Rocky Linux and where we support Rocky Linux. In addition, we have, and we just announced an S3 API interface support through a gateway. So it'll come through our gateway side, SMB and NFS support. And then we have a couple ancillary software products that help you to tie this all together relative to analytics and data movement. One of the more seminal patents that we have in our company is on a per-file erasure coding. So this is unique in the marketplace and allows us to have granularity to the file level if just in terms of being able to do things like set a RAID level, a erasure code level at a file level, it gives you a lot of flexibility, provides you a lot of fault tolerance capability. The way we manifest our software is we use storage nodes and we use director nodes. So this is all the metadata management is happening on the director nodes. All the data itself and all the metadata itself is being loaded on our storage, and we call these storage object stores. So this is my story here about where we see the modern HPC. So I think everybody's familiar with traditional HPC being more modeling and simulation type workloads, computer engineering, computational fluid dynamics. And then we saw this migration happening, this integration happening between things like big data and Hadoop and analytics being incorporated into HPC. So HPC had this new definition that said it's not just traditional modeling simulation in the national labs and those type of places, but it's actually being used for analytics as well. And then I like to quote a couple guys at NVIDIA who actually coined a term on this HPC and AI. So it's the first level integration of HPC and AI, where effectively you're doing pre-processing, you do some computation, you can do some post-processing, and in this computation method you will like break out and do some AI and come back, and we'll talk about how this is changing, and we're working with different partners in terms of something that's called augmented AI. I think I'm touching the mute button. And so this is all happening on-prem, it's happening at the edge, it's happening in the cloud, and so Nicholas Dubé from HPE actually coined this term that I really like, which is HPC and Internet of Workflows, and it's really the changes you're going to be seeing happening throughout any kind of design industry today, that you can actually have integrated AI, meaning that you can simulate, like if you wanted to do a CFD flow and you wanted to do, you can simulate your data, and it'll get you, instead of doing this wide variance in terms of where your simulation and what your accuracy and how you're going to close off on it, you can simulate your data, you can train on that data and help you point in the right direction and save you a couple orders of magnitude of time in terms of getting to your solution. And an analogy I use is like you're driving on the roadway and you're on Surface Street and you don't know, you're kind of figuring out where your destination is, and you hop on the freeway and you get you all the way to the nearest exit and you get off and you still have to do your closure at the end, but meanwhile you save so much time in being able to get there. Except in Southern California where we know that there are traffic. So here's my little story. There was a time where we were building an automated highway system. I was actually working on a project that was part of a big conglomerate of people with Caltrans and GTE back then and all. And it was going to be the automated highway system that was going to deploy like in 2025 or 2015. And it needed all this infrastructure in place. So anything for collision avoidance, anything for latitude and longitudinal control of your vehicles, and at that time the technology, trying to use vision technology combined with, we were actually using ceramic tiles on the road to be able to give you a latitude control, and of course you had all the different lidars and lasers and radar technology to give you the control for the longitudinal control. And then we're using things simple like on-ramp and metering and stuff to try to keep the flow going. So this is an optimization problem, and it's not unlike an optimization problem for me when we look at HPC storage. So you think of that and you think about what are the things that you need to worry about. You need to worry about reliability, the robustness of the system. You need to worry about things like flow control. You need to worry about self-healing. So I actually did like a failure modes analysis on an just like an intersection today is optimized for you to have rear-end collisions, not to have head-on collisions. In an automated highway system, the idea was to have no massive, just like airlines and stuff, no massive collisions, and to be able to have this idea of platooning vehicles together. You do the spontaneous platooning, but you limit the number of vehicles that can be together, and then you have this sort of like this distributed system that allow you to be able to program your navigation system. And there are many pundits who ended up saying this type of stuff is called a railroad system, because you actually gang railroad cars together and all. But this was like being rolled out in Germany with the Freightliner trucks and all, and being able to create these big platoons of trucks down the highway to get better efficiency. So with that segue, this goes down to, in that premise of how do you build a system, for us a storage system, so we have some core values that so back in the day when parallel file system was just happening and GPFS was out there and it was running on AIX, and we were working with Lustre to try to get commercial parallel file systems to the market. The primary thing was to have an ease of use scenario so that hands-off administration. We have customers who say it just works, we don't even think about it. 99.9, 3 nines, more uptime, and everything is about being able to make it easy to use. But that's based on having something that's resilient and being able to have a system that had a shared nothing with no single point of failures system, self-healing, our file level erasure coding. Those two come together, and of course the main thing that in the parallel file system that you want to have is a high performance, high capacity, unlimited capacity. How much can you scale? How much can you get performance? The other thing that we actually added in for our hybrid solution was this great technology, and I'll show you in just a second. It's an intelligent placement technology we call dynamic data acceleration, to take advantage of the hardware that's available. And for us, that means that if you have small files, you put them on SSDs, you put large files, you put them on hard drives, you have metadata, NVMe flash, so you're trying to optimize whatever media you have available for you in the system as it gets deployed. So PanFS is our bread and butter. It's our software. But it's more than a file system. It includes a whole software suite, and we have a active manager product that allows you to be able to set different levels of alerts and of just email feedback to the administrators. We have security that we launched a couple of years in terms of a hardware-based encryption. So the idea is that to let your compute nodes, to be able to optimize its performance. And so we use a secure encrypted drive technology, and we worked with key manager companies like Thales and Intrust to be able to provide an integrated solution so that you can actually have the key managements working with encryption at rest. We also support SE Linux, so we have file security label support. And then I talked about these two different products that we have for mobility and for visibility. So the idea is that you can know everything in your network, our product, but everything else. So if you want to move data around, and if you want to set, from a mobility point of view, you want to set policies for retention levels, you want to move stuff to the cloud, we support S3 and Swift, and I'll talk about, that's like, we can store things from our PanFS system into the cloud, and I've got a great eye chart for you later that will show all this in place. So this is my first complicated slide, but it's just to show you that how we, in trying to figure out, to let you know, our job is to try to make any system administrator's job so simple. And how do you do that is you prevent hotspots. And how do you do that kind of thing? So we start off from the left here. We do file level erasure. So every file comes in, we turn it into object components, and we add the P and Q. So we do a 2 parity value system, and we use like RAID level terminology layout. So you can use RAID 5 or RAID 6, and that depends on how many parity you're going to do. And typically for the smaller files, we will do replication because erasure coding doesn't really help with smaller files. And so you could do, but we'll use a standard XOR for 5, and then XOR plus a Reed-Solomon for RAID 6. So 2 parity, really RAID 6 just means 2 parity in that context. And then we spread it across our networks, and we try to use what we call a distinct uniform random distribution, right? So this aggregated solution, try to keep things level it out. And then we do this active capacity balancing especially when you have reconstruction happening, if something fails and we're like fixing things on the fly, to keep the system balanced, and that's to make sure that there are no hotspots. And then I talked about this, we have NVDIMMs and NVMe SSDs, and the idea is to be able to leverage the media that we have available to us. And then at the very tail end, then we want, if you as a system administrator want to move files to different archived levels, to different cloud, different S3 objects, then we provide that capability. So we instantiate our PanFS software on appliances today. And we have a family of appliances, different hybrid products. We have an all-flash product, and we have some smaller capacity products. One of the announcements that we made at the show today is working with Seagate. Seagate announced collaboration with us on using their dual actuator SATA drives. So effectively, you have one disk drive now that has 2 actuators on it, and you get double the IOPS, double the throughput off of it, and effectively for the same price. And it's fairly much a drop and replace. We had to do some software, obviously, to integrate with it, and they've done a lot of ecosystem work to get all the Linux stack and controller companies on board. But the idea is that that you will effectively have, with the SAS drive, 2 LUNs that would appear, and we now address them as 2 separate ports for us to be able to use them in our system like we do with SAS drives. We have our Director products, and we also have, these are all Ethernet based. They have 2 dual 25 gig Ethernet ports on them. And then if you're running InfiniBand on the front end, we ourselves have a InfiniBand router. So it's InfiniBand on one side, Ethernet on the other, so that you can route InfiniBand based compute cluster information down to the storage side. We also work with Cornelis Networks on OmniPath as a separate fabric. So they have OmniPath HCAs and OmniPath switches, and as well as in OmniPath routers. So this is my big diagram to show you and where we're. So if you look at where we sit and you're running these applications, so DirectFlow Client for us is it's a direct and parallel access from the clients in POSIX, so it's cache coherent from the clients, access to all the storage that gets distributed. This data that gets distributed as we talked about with the per file erasure coding across these. If any of these drives or anything would fail, we would reconstruct that drive that was being failed while the system is still running. If you're using other protocols like NFS, S3, and SMB, they'll come in through our gateway services. So if, for example, you wanted to if you had written something to a Ceph storage and it was using S3, and now you wanted to use that same application and talk to PanFS storage, then you can come through our gateway service and use that application and come in and talk to PanFS. Similarly, you can take our PanFS and you can send each file up and becomes an object in the cloud. So in Azure, Blob, Google File Store, AWS S3, or any Swift or S3 cloud instance, or any private cloud object store instance. And if you're writing like microservices-based cloud-native applications, you can talk to these objects here through a REST API. So to be able to move this faster, we use our technology partner Tempo and all to use their concept of data movers. And these data movers all support Rocky Linux, as well as do our compute clients for NFS, SMB, as well as S3, and for our DirectFlow client that you can run on Rocky Linux. And that's pretty much it. So call to action, please stop by our booth. You're here already in the CIQ booth. Go to Seagate's booth to learn more about this dual actuator. This is like really groundbreaking type technology in terms of just doubling the performance just using multiple actuators. And of course, one of the things that I was talking about earlier with Altair had launched their HyperWorks product that allows this integrated AI workflow through their through the HyperWorks product, and they're in booth 825. Are there any questions? Any tests? Anybody know what parallel file system is? Okay, thank you very much. I appreciate it.
the overview of that. And we are partners with CIQ as part of Rocky Linux and delivering kind of high performance solutions in terms of storage and like AMD servers and Rocky Linux, and that's combined. And then we are the application that sits on top of that. So I'll give you a little information about the company. This is a table of contents because we have a ton of tools, right? We have lots of different tools. If you're doing any kind of genomic data analysis at all, there's different applications for that. I'll skip over most of those, but we can talk about them. So at Sention, our mission is to enable precision data for precision medicine, and what that means to us is giving our customers the opportunity to process that data in an extremely accurate, efficient, and cost-effective way. And we do that based on our engineering team and scalable and accurate algorithms. Our core strength is accurately and efficiently solving math problems in computers. And a lot of people would say this is a supercomputing conference, and a lot of people have that core strength. I would say one of our employees was the #1 physics student in all of China in 1988. And he was 2 years younger than everyone else who was taking that physics test. And he's a big contributor to FreeBSD, which I guess is now the Apple operating system. So he used to make free processing, put it through a genomic sequencer. Our data or our software will help you process it. So the company has been around. It's been founded in 2014 in the Bay Area. I'm lucky enough to live here in Denver. I hope you've all been enjoying the beautiful weather here. It's a little warm for this time of year, but it is typically sunny like this. Let me know if you want a restaurant recommendation. I can give you a lot of that as well. So like I said, we run on any CPU or ARM. We work very well on top of whatever Linux you're using. CIQ is a great partner of ours. And we provide, I'm the head of business development, and we provide a very friendly, I leave you alone and you leave me alone, which is good. But also we've won many awards in both that, because now our field has an opportunity to grade the accuracy better than it did when we started 8 years ago. But when we started, we wanted to say, if you like your pipeline, you can keep your pipeline. You just have better compute algorithms that are realizing the same math. So we basically have a per core efficiency improvement of generally like 5 to 10x per step. And then we also have a better software implementation. So it's self-contained, it uses lower RAM, and it's automatically parallelizable to whatever size machine you have. And then also what helps with that, right, is there's no thread dependency. So a lot of the other tools also have thread dependency. They're downsampling. That's kind of part of the consistency challenges. And I mean, the software works great, but we're also here to support you to kind of let you know why the tools are calling the data in a certain way or whatever. So typically the support is on the results, like helping a customer understand the results or understanding the tools and pipelines. This is a command line based software, so there's a lot of detail in the manual, and I tell people to use our support team like the manual, which they're okay with. They don't love it, but I'm sure you guys understand. Also, another thing to kind of highlight in that scalability, and this is also why we have consistency, is we have no downsampling because we've been able to handle high-depth data better. So the other tools in the field basically can't part of what's going on is a hidden Markov model where they're looking at all of these strings of 150 base pairs. So that's like a read, and you generate, basically these machines will generate like billions of reads a day now. But in your genome, all these 150 strings could get stacked up into a coverage of 30x, which many tools will be able to do. But some applications you want to sequence deeper, so you might want to sequence 1,000x or 10,000x or even 100,000x. And in that case, all the reads like under a region are kind of looked at in the context of each other. So then the compute problem really explodes, and our team is able to handle that very efficiently. So we don't do any downsampling, and it still run 5 or 10 times faster. Also, so this is kind of the main goal of bioinformatics analysis software, right? And maybe this is also, if you're familiar with other HPC data processing, these are similar things that you want to be good at. So one is if you're accurate and consistent, which we are. We've won awards on this, and this can all be verified. Also, just efficiently meet your turnaround time goals. Our software is distributable onto as many servers as someone would want, which I don't really recommend because it already does a great job on single servers typically. And also it scales down when people have like a BRCA panel, like a smaller gene panel, which is also very useful in the cloud where if you're processing lots of tiny jobs, you don't want to put those on a giant server. You can just put them on smaller servers. So our software really scales up and down, so you can efficiently meet whatever turnaround time you need, either locally or in the cloud, with an extremely low total cost of ownership. This is not bioinformatics is not like a crazy money thing, right? It's more the Lord's work, and then luckily that these engineers, like people say, where are the engineers who are really good who are solving this problem? And they're at our main competitor, Illumina. That's also good. It's a good product, the Dragon system. And then I'd say we are the other best software in the world for this. And we are the best sequencer agnostic software in the world by far. Illumina is kind of trying to do a walled garden approach, right? And say, start with this kind of freemium model and then pay us and go into our platform, right? So those are kind of the two good options, I would say. And if you're not using one of those two options, then you should definitely talk to me. And you can talk to me also if you're using the Illumina Dragon system, as that's our primary competitor that we do, compete well against all the time. And like I said, multi-platform and super easy to use as far as enterprise software goes. I am not a software engineer, so I can run it like in the bash, but not super well. But I talk to our customers all the time, and they're always extremely pleasantly surprised with how nice it is. Hey, Glenn. So now we're going to just start skipping through some stuff because this is like a long thing. Here's just one example, though, of just pipeline complexity. So another tool that we compete with is, or we replace, is just the open source BWA GATK. So we have made usage improvements when we can in the command line. So you can see in this, like GATK has 3,400 lines that are used, and we only have 567. So there is less headache, less scripting involved. And we also are working on releasing, we provide you kind of example scripts to use, but we're also working on, as our world has kind of gotten a lot bigger and we're supporting more than just Illumina, and we have kind of complex PacBio pipelines, complex Oxford Nanopore pipelines. We're wrapping that kind of stuff up into Python so that the user can say, great, like run the PacBio script or run the element bio, whatever it is. So we are improving our usability beyond this. Here's a quote, though, from one of our customers. Everyone in America has heard of Mayo Clinic. So we use that as a, hey, like Mayo Clinic likes it and wrote a paper about it. And in their paper, this is more of a computer science speed up. We're not 50 times faster. Depends where you measure from and what you're measuring. Here's another example. This is kind of also what I was talking about. This is some work we did with Intel. The benchmark, it was taking us 12.9 minutes, so over 1 minute faster than the H100 and about 22 times cheaper. And the NVIDIA is a good system relative to the BWA GATK open source tools, provided you have GPUs. But with us, you don't need GPUs. Also, we have, I mentioned before, an improved accuracy tool. So we have, if you want to run a BWA GATK pipeline, we have that accelerated, kind of like a software accelerated pipeline, and Mutex 2 and joint calling and all of those different things. But we also have a more accurate tool, which basically has an improved local assembler and some machine learning. And that's what we use for people who are more into accuracy than matching. And again, we support a lot of different sequencers. So this is one example of a new sequencer, and the data is quite a bit different. And so We partnered with them, and they also partnered with the Broad Institute to kind of develop a pipeline specifically for their sequence data types. And you can see we're in the red here, while the Broad Institute tool is in the blue. And you can just see we have a significant accuracy improvement relative to kind of the Broad Institute's best effort for this. And then also, I think we're around 8 times more efficient per thread compared to that solution. It costs us about $1 on demand to process a 40x Ultima BAM. Here's some old benchmarks. This kind of, I already mentioned it a bunch because I'm excited about this 12.9 minutes one, but this is all basically our new release combined with the new servers available on Amazon or available locally, right? The servers have gotten better over the last year. Our software's gotten better over the last year. So, based on these numbers, it's about the lowest we've seen is on ARM. We can process a genome in 83 cents on a current ARM server in Amazon, and that takes maybe 35 or 40 minutes, something like that. While, again, with the latest AMD machines, it could be 13 minutes. And obviously, if you wanted to process genomes in 5 minutes, you could split it and do that if you'd like. And then it would cost, let's just say it's double, right? So it's $3 instead of $1.50, and it's 5 minutes now, or whatever. I think that's fast enough, personally. And then also, just it works across all instances. Just like I said, we support ARM and x86, so whatever instance you want to run in Amazon, whatever cluster you have locally, and our license is just a time-based license, so you can have as many software licenses running either locally or in whatever clouds you want. I don't care. So it's one simple contract with Sention that I do with you, and then we don't have to talk for a year or 2 years or 3 years, which 3 year depends, or one, or a free trial for 15 minutes or something. And then I just want to go to we have lots of applications that go into. This is one, though, that and long reads. According to this data, we have the most accurate structural variant caller in the world. It's just a little better than this other good tool called Sniffles 2 that my friend develops at his lab at Baylor. And then there are other tools. And you can also see that a lot of the tools degrade as coverage goes down, and coverage kind of equals money. So people do want to optimize on how much coverage they're doing. But that's in long reads. We've won a bunch of awards in long reads for accuracy. It's also much more, all of our tools, they're faster, and they also are generally require lower RAM, which is nice. Some people will say, I've accelerated some algorithm, but now instead of 64 gigs of RAM, I need 2 terabytes of RAM. We actually use less RAM, and you can see in this example on the right, this is an independent benchmark, and they're testing Google's deep variant, the noisy data potentially. I would recommend them. Also, here's another example of just pipeline runtime. So pipelines, and this is the structural variant calling, this orange one to there. So you can see our structural variant caller is extremely fast. And then here's an example of the pipeline where the blue is the alignment time. So that's kind of the open source best tool for PacBio, I would say, which is Minimap 2 plus deep variant from Google. And here's ours, which is our Sention Minimap 2, which we've accelerated by about 5x relative to this. And then we have a much more efficient variant calling strategy as well. And they're both very accurate. We're generally a little more accurate, but I'm not here to quibble over, whatever, 1,000 variants or something. They're both good. They're both good from the accuracy side, I would say. Let's see. Some of my other favorite slides. This is oncology. We do that great. This is one of my favorite slides. I think we have there's these UMI tools. This is kind of like tagging of the data, and we have developed an extremely efficient, accurate UMI tool. This is a lot for liquid biopsies, but really whatever UMIs you want. We also just published a thing with Charité, which I'm told is the Harvard of Germany. I don't know if I hadn't heard of it before though. But I only knew about maybe 2 universities in Germany before then, and I'm half German. But anyway, we just published a thing with Charity where we accelerated something they were working on with Oxford Nanopore by like 14x with Intel. And part of that was we actually adapted this tool, this ctDNA pipeline UMI tool, to do single-cell RNA-seq. So basically, if you're doing any kind of genomic application, know about Sention and come reach out to us if you're interested in a free trial now or anytime in the future. Genomics is there's people with pipelines that they haven't updated for 6 years, and that's fine. But when you do want to consider updating them, come talk to me. And again, I want to thank CIQ for having me. They've been a great partner. And I don't know, I would take any questions if anyone has any. Yeah, I just based it on Amazon pricing because it's kind of the most, you can just do it, right? Versus saying, if I buy this, or I don't know if that's what you're alluding to or not, but like if I buy this server locally, like what is my depreciation? I have all these servers, and if I'm running them at 100% of the time or 80% of the time or whatever. So obviously you can drive that cost down by owning yourself. I personally think the bigger issue with the cloud rate is the long-term storage. Right, the genomes are big data. They are, it depends how you want to store them, but they're, compressed generally like 40 gigs. So it's really I think the bigger issue is where do you want to store your data long term, and wherever you want to process it, we're basically taking your compute cost almost to zero, because especially if you're doing like other small panels or exomes, right? Those are 8 cents or something. But yeah, again, on Amazon, we would process a 30x short read genome with alignment and variant calling for, 80 some cents to, $2.50, kind of depending on the instance you're deploying it on. And that's all on-demand prices. So then there's also the spot market, which my general rule of thumb there is just cut it in half by 50%. It should be, and because we're running this so fast, it enables the spot market better, right? So because it's already only 35 minutes. So like that's a lot easier to then get that 50% savings relative to being like, oh, it cost me $7, and now I'm trying to use the spot market to do it in $3.50, and then you're chunking it up and trying to keep things rolling. Whereas this is, you only need the spot market to be on for you to complete the job in, between 15 and 40 minutes per instance, per sample of 30x genome. Obviously, much tinier if you're running, a genome is 3 billion base pairs long, whereas you might be running 4,000 base pairs, and then it'll be done in, no time. Anything else? What storage solution are our fast? So we just support all the open storage or whatever. Like what we support all the current file formats. So it's not like we don't use a different file format or anything. But so there's your FASTQ file, which you can zip, and you can also do reference-based compression. You can do different things with that. Usually, we recommend, and people like to keep the CRAM file. So all of there's the BAM file, which is the non-compressed version of and then there's CRAM file, which I guess maybe stands for compressed. So the CRAM file people like because then you can see kind of the alignment of kind of what the variant caller was looking at. It doesn't show you. There's a little in the weeds there where you could actually have our tool process out exactly what the variant caller is seeing. But the CRAM file is storing at least what the alignment is seeing. And then a lot of bioinformaticians like to look at that by eye. So storing the CRAM file is definitely what we would typically recommend. So our software tends to be it consumes the data pretty quickly. So as long as if the I'm not that familiar with like networking. So if what I know is our software, we want to have like the local SSDs or enough speed in your storage, in your I/O, to be like local SSDs. We also have done some things where, like I mentioned, we're low RAM. So some of these new instances have enough RAM to where we just use the RAM as the local storage, if that makes sense. So it just depends on, what your goal is. And you can optimize, like the software will fit to what structure, you have. Yeah, thank you. We have SnakeMake. We don't support a Nextflow implementation ourselves. There are also some kind of open source consortiums that are working on. We were supported in the old Nextflow, and then Nextflow got upgraded in the SARIC consortium, and now they're working on adding us back into that. And then I don't know if you were here before, we're working on a Python implementation that then you could just put into your Nextflow, so it will all just run for you. So we are working on improving the efficiency. We do have WDLs because of our work with Amazon Omics. So we're integrated into Amazon Omics as one of their main partners. So you can also run our tools there from a like an API call that'll just run a pipeline. But in that, we've also developed WDLs that are publicly available. So there are Nextflow, SnakeMake, WDL, CWL. There are many workflow manager or job description languages, and our tools are designed to work with all of them, and we can help you at least get you started with all of them. But as a small company, we don't support most of them as a commercial product, if that makes sense. All right. Well, thank you for your attention. I hope you're having a lovely supercomputing conference. Oh, and yeah, talk to me afterwards if you'd like. Hello, hello, hello.
Test, 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 test. Testing, 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 testing. Yo. Bless you.
Submitted.
Probably when he did that.
CIQ, we do Rocky Linux. Doing a live webinar. You guys want to talk about what you did? How it went? All right.
We good, Alex? So welcome to SC23, and this is a student competition. And we're here with Boston University, Brown University, and UMass. B3, just finished the competition. How did it go?
Definitely a little rough at the beginning. We had some obstacles with shipping the computer, actually. Maybe like day one of like 4 p.m. or something. So while everyone was setting up their computers, we were kind of just twiddling with our fingers because our vendor messed up. But once we got everything set up, things were working smoothly. Some like errors on MPI installation, but we got everything to be working, I think.
That's fantastic. You want to tell everybody your name?
Yeah, I'm David.
Where are you from?
I'm from New York, and I go to Boston University.
Excellent. Well, thank you very much. So have you had a good time so far this week? Have you just been focused on this the whole time?
Yeah, honestly, it's been really exhausting. Some all-nighters, but yeah, I feel good. That's over.
Good. Now what are you going to do?
Get some food, get some rest, celebrate with the team.
That's awesome.
Yeah.
Very good.
Thank you.
How about you guys? How do you think this week went?
Yeah, once we got our actual cluster set up with us, things were pretty much smooth from there. Kind of, we'd seen most of the applications before as they gave it to us, and we kind of just did our thing. But then the mystery app did throw us for a loop, really different content than what we were expecting. And
Whenever you talk about the applications that they give you, so explain to everybody kind of what that means.
yeah, so I guess with the competition, there's the benchmarks and applications, and the applications are sort of high performance computing things. One that I worked mainly on was 3D MHD. It was a magnetohydrodynamic simulation. So obviously, like with all the physics and everything, there's a lot of computations that need to be done. So it's an HPC application, and all we really need to do is compile it and then sort of set up the parameters so that we could run it as fast as possible given our hardware. And yeah, there was just a lot of testing around, like playing around with numbers and trying to just optimize our time.
That's fantastic. You want to tell everybody your name, where you're from?
Yeah, I'm Schamer, also from New York, and I also go to Boston University.
That's great. Thank you very much. So what did you think about Rocky?
I think it was pretty much what I'm used to working with. And
No issues?
no issues on like the OS part.
Good.
I guess we were kind of new with sort of server level things. So there's like a BMC controller that apparently we had as a security vulnerability, and that's our bad. But you know, you learn.
Absolutely. You gonna do it again next year?
Hopefully so. Yeah, I have one more year left of school, and I'd like to revisit this.
It's fantastic. What are you thinking about doing after school?
Well, as for the competition, it's only available for undergrads, so no more competition, but high performance computing, I guess, is something that'll always be on my mind. I am somewhat in more software interest aligned, so I'll see where I go.
That's great. Have you had a chance to walk around the floor since you've been here, or is that what you get to do? Maybe now you can go look around.
Well, yeah, with it, running the applications, you kind of, after you press the run button, you kind of sit and wait. So I've had some time to look around, collect some merch, and it's been a good week so far.
That's great. What did you see out there that was interesting to you?
Some of the talks, they just, a lot of certain HPC applications where it's like making energy efficiency and just bringing computing power to just users through cloud, which is really interesting, like being able to train a model even if you don't have hardware yourself. So really cool things.
That's fantastic. Well, thank you very much, and congratulations on finishing. That's great. Thank you. Appreciate it. Did you guys get shirts? Rocky shirts, stickers?